regulators.
Well, good morning, good afternoon, or good evening, depending on what time of day it is that you're watching this video. In this lesson here, I'm going to go over with you how to find the volume of a solid that results from revolving a region about a line. Okay, so this is called the disk washer method, because sometimes we're going to make disks, sometimes we're going to make washers. Okay, and a disk is just a solid circle. All right, if we revolve it around this thing solid, we get a disk. A washer is going to be if we revolve it around and we get something that's circular, but inside of it we have a little or smaller circle. Whoops, I hit the wrong thing there. I meant to do a circle here. Okay, that would be a washer. Okay, so it's real important that we know how to find the area of a circle, right? And if we make a disk, if we've got a solid circle, then the area of a circle is just pi times the radius squared, right? If we're going to fill in, the thing we're doing encompasses all of this right here, right? If it's a washer, then we're only doing this region around. We're making circles like this that are sort of hollowed out in the middle. Okay, so when we do a disk, the area of a circle is just pi times the radius squared. Right? If we have a washer, then we've got a big circle with a little circle, so we do pi times the big radius squared minus pi times the little radius squared. Okay, and that's where these two formulas come from. So this first one says the volume equals pi times the integral from a to b of the quantity capital R of x squared minus little r of x squared. And we do it with respect to x. That's whenever we have a horizontal axis of revolution. Okay, a horizontal line like that. If we go about something like that, we make circles, and we're going to do everything in terms of x. Okay, now this capital R is the distance between the axis of revolution and the function farthest from it. That would be our big radius. The little r is our little radius. That's the distance between the axis of revolution and the function nearest to it. And then if the region is flush to the axis of revolution, then the r is 0. Okay, and flush means right up against. So if our region is right up against our axis of revolution, we're going to make a disk. We're not going to have to hollow out little circles. If it's not, then we're going to have some little r, and we're going to make washers. Okay, now if it's a vertical, we're going about a vertical line, something like this, then we do the exact same thing, but everything's in terms of y. Okay, so a horizontal axis of revolution, I do it in terms of x. Vertical axis of revolution, do it in terms of y. And if you look at the formula here, it's just pi, then you get the integral times r squared. So it's really just the area of a circle. All right, if I took the pi, just to illustrate here, if I took this pi and distributed it back through here, right, I get pi times the big radius squared, makes my big circles, and then minus pi times the little radius squared makes my little circles. Okay. So when we do this formula, this is just the area of a circle, and then when we integrate it from a to b, it adds up the area of every circle from a to b, adds them together, and gives us the solid volume. Okay, so let's actually, I got an idea here. I'm going to go on the Google machine. All right, so what I've done here is I went on the Google machine, and I just Googled volume disk washer animations, and I clicked videos, and look at this. Within 0.32 seconds, it found 35,900 videos I could watch to sort of see what's going on here. And maybe we'll just go with this first one. You know, hopefully the first one's a good one. Let's watch this here. All right, I was trying to see if I can get this to fit in the window better, but let's just watch it here. So we've got the function y equals the square root of x. Okay, so if we graph it, it just looks something like that. And then we've also got the function y equals 1/10 x. So that's just a line that goes through the origin with a slope of 1/10. It would look something like that. Okay, it looks like in this example, then we're also going to do x equals 4. That's just a vertical line. So we're going to take that region and revolve it about the x-axis. So we get something that looks like that. And let's see here, when they turn this thing around, if they split it, it's like that right there, because that's a washer, right? Every cross section, if we split it, is a washer. We've got this big circle, and it's hollowed out with this little circle in here. So if we were going to find the volume of this, we would use the disk washer method. Yeah, but this right here is more or less just for us to see an illustration of what this thing would look like when we go about the axis. And actually, you know what we might as well do while we're here? You guys, why don't we, I'm going to take a picture of this. Didn't think about this till right now, but this is a great thing about math and life, right? You can just monitor and adjust things as you go. I'm going to take a picture of that. Why don't we go ahead right here and find the volume of this resulting figure? So what we've done is we've taken the graph of y equals square root of x, the region bounded by the graphs of y equals square root of x, y equals 1 over 10x, and x equals 4. We've revolved it about the x-axis. Now we're going to find the resulting volume. Okay. So let's say I was doing this, and I didn't already have this illustration. I would do just like they did. Whoop, what's going on here? Let go of that. All right, I would sketch this region. All right, so here's my x and here's my y-axis. And let's see. Square root of x looks something like that. 1/10 x is just a line that would do something like that. I'm going to make it a little steeper here just for illustrative purposes. Okay, it does something like that. And then let's say x equals 4 is right here. So this is the graph y equals the square root of x. This is y equals 1/10 x. And this is x equals 4. So what we're going to do is we're going to take this region right here. Yellow doesn't show up real good. Maybe I'll do it in this light green. We're going to take this region right here and revolve it about the x-axis. So we're going to go about the x-axis, and we're going to get this solid shape. So if I was doing this without already watching this little video, I would think of something like this. Look something like that, and then this is going to be circular shaped here, right? And we're going to have a hole in the middle because it's not flush right there. So what I'm going to do, it's a horizontal axis of revolution. So I'm going to use the disk washer method and do everything in terms of x. So I'm going to have pi times integral. In terms of x, my shaded region here goes from 0 to 4. So I'm going to go from 0 to 4. And again, the reason I got this pi out here is because I'm finding the area of circles. The area of a circle is pi times the radius squared. So now I got to figure out my big radius, and then it's not flush to the axis of revolution, so I subtract out my little radius. And then I integrate that with respect to x. Okay. Now, if I come over here, the radii or the radius of a big circle is going to be from there to there. Right? This figure goes like that, which we can see here as it went around. So from here to here, I need to figure out what's the length of one of these red lines, because those are going to make my big circles. Well, they're bounded on top by the function square root of x, and they're bounded on the bottom by 1/10 x. So that's just going to be the square root of x minus 1/10 x. Maybe I'll write as x over 10. Right, because we take the y on top minus the y on bottom. Actually, I take this back. Almost made a careless mistake here. My red lines go all the way from the square root of x all the way to the x-axis. On the x-axis, y equals 0. So they're going from this y, which anywhere on this curve, y is square root of x, to y equals 0. So the big radii are just the square root of x. The little radii, the things that hollow out would be these blue lines right here. Because then we have these blue circles that come in here that hollow it out. Right? That's what put the holes in it here. So if I draw a blue line here, that's the radius of my little circles. Well, that would be just from y here to y's here. So anywhere on this line, y is 1 over 10x, and on the x-axis, y is 0. So my little radii are just 1 over 10x. Now I can go ahead and work this out. We got pi times the integral from 0 to 4. And then if I square the square root of x, I get x. Minus square this, I get 1 over 100 x squared. Then I integrate that with respect to x. And now it's just integration, right? The new thing was setting up our integral. So antiderivative of x would be 1/2 x squared minus, this is going to be, I almost took a derivative there. I'm going to add 1 to the exponent and get x to the third. Then I'm going to divide by 3. So I'm going to wind up with x to the third over 300. And I do that from 0 to 4. So now I've got pi times, plug 4 in there, I get 16. Half of 16 is 8. Minus 4 cubed is 64 over 300. Right now this is just reducing a fraction. Let's see. I think 4 goes into 8 minus 4 is going to go into 64 16 times. It's going to 375 times. And I don't think that's going to reduce. So I can think of the 8. Let's go with the mixed number. 8 is going to be 7 and 75 over 75. And I subtract 16 over 75. And I get pi times 7, and then 75 minus 16 would be 59 over 75. So I'd say the volume of that shape, it's sort of a weird number, but you know, who are we to say what's weird? It's 7 and 59 over 75 times pi. Okay, now I could have also done this on the calculator. All right, once I got my setup here, I could just plug that in the calculator. And let's check this. I'm going to leave the pi out for right now. So I'm going to go to the main menu, and I'm going to go to Options, Calculate, Integrate, and I'm going to do x minus x squared over 100, and ask the calculator to do it from 0 to 4. $584 over 75, which got a feeling that's 7 and 59 over 75, but let's check. What's that as a decimal? 7.778. If I do 7 plus 59 over 75, whoops, over 75, look at that. Deja vu all over again. So it was pretty cool. We just found a random example, a random thing on the internet there, and we found the volume of it from our figure. Okay, I could go back here. Unfortunately, they don't give me the answer, but I could look at some other videos too. There's other animations to show me what these shapes would look like. So you guys, I'm going to be honest with you. As I go through and do these, and I draw them, I'm not real artistic when it comes to drawing 3D shapes and figures. Okay, so I'm going to do my best. But out of curiosity here, I'm going to look at this one right here real quick. What's this one look like? Well, they're doing it in 3 dimensions. Let's not do that. Let's just stick with what we're doing here. All right. Let's do some examples like this one right here. Let's find the volume of the solid formed by revolving the region between the curves y equals x squared, y equals 0, x equals 0, and x equals 1 about the x-axis. Okay. So another one about the x-axis. And you guys, I'm a big believer in sketching this to see what it looks like. So x squared is just a parabola. It does something like that. Y equals 0 is the x-axis. X equals 0 is the y-axis. And then x equals 1 would be about, let's say, right here. So our boundaries are y equals x squared, y equals 0, x equals 1, and x equals 0. So the region we're talking about is right here. And again, that yellow doesn't show up real good. I'll start keeping, whoops, I don't want the crayon. With this light bluish green here, teal or whatever this is. That's our region right there. Okay, we're going to revolve that about the x-axis. Okay, so when it's about the x-axis, we can keep things in terms of x. So it's going to be pi times interval. In terms of x, we're going from 0 to 1. And now this is nice and flush to the axis of revolution. All right, there's no space between the x-axis and our region. So we're going to have disks here. We're not going to have to hollow it out. So all I got to do now is figure out if I draw a line from here to here, right? That's the radius of the circles this thing's going to make. Because this is going to make like a cone-shaped thing like this. That's just going to go in like this, and the circles are going to get smaller. But it's going to be solid. So the radius of these circles, or one of these circles, is just from here to here. So it's whatever y is right here, which is x squared, to y equals 0. So the radius of my circles is just x squared. And the area of a circle is pi times the radius squared. So I'm going to do x squared squared and integrate it with respect to x. So I'm going to get pi times the integral from 0 to 1 of x to the 4th. Integrate that, and I get 1/5 x to the 5th. And I do it from 0 to 1. And this is really nice. Plug 1 in there, we get 1/5. Plug in 0, we get 0. So this is just pi over 5. So the volume would be pi over 5, or 1/5 pi, cubic measurements. Right? And they're not telling us if they're feet, inches, meters, whatever. So I'm not going to write cubic units. We know it's cubic because we're finding the volume. If they gave us measurements, then we'd use that, cubic of that. All right, let's keep rolling here. Oh yeah, we like this. Let's do one with some trig here. Let's find the volume of the solid formed by revolving the region bounded by y equals tangent of x, x equals 0, and y equals 1 over square root of 3 about the x-axis. Okay, again, I'm going to sketch this. Now, tangent, I remember from my trig days, is one where we've got these asymptotes, and it just comes in like this, and it looks like x cubed. And then it just keeps doing it over and over. Right, and there's asymptotes in between here. Now, I'm fairly certain here with the region they're giving us, though, we just need this first part here. So this is the graph of y equals tangent of x. X equals 0 is the y-axis. And then also we've got y equals 1 over square root of 3, which would be maybe a line that came through like that. There's y equals 1 over square root of 3. So the region we're talking about here is this region right here. All right, we want to find the volume if we took this region and revolved it about the x-axis. Okay. So looking at this, here's the x-axis. This region isn't always flush or right up against the x-axis. So I'm going to have to do the disk washer. All right, so I'm going to have pi times integral. This region starts at 0. I'm going to have to figure out where it ends, right? It ends right here, so we might as well do that right there. We got to figure out what x equals right there. Well, that's where 1 over square root of 3 intersects with tangent of x. So I got to figure out where does tangent of x equal 1 over square root of 3. All right, so if my memory serves me correct, that's at 60 degrees, or pi over 6. All right, if I draw my friend the 30, 60, 90 triangle here to confirm my thought process, This goes square root of 3 to 1. And look at that, because I think I was thinking it backwards. The tangent of 30 is 1 over square root of 3. And 30 is pi over 6. So right there, x equals pi over 6. So here we're going to integrate from 0 to pi over 6. And now we're going to have to figure out what's our big radius, what's the radius of the big circles, and then subtract the radius of the little circles and integrate it with respect to x. So I come over here, let's say maybe in red, I'll draw the radius of my big circles, or maybe I'll do this purplish one here. All right, my big circles are going to go from here to here. Because again, if I sketch this, we'd have something that comes out like this, right? And this region's here. We're going about the y-axis, so we're going to get things, big circle, it looks like that, but then it's going to be hollowed out. So my big circles are going to have a radius that goes from here to here. So the value of y right here to the value of y right here. Well, anywhere here, when I draw these big radii, y is 1 over square root of 3. And then here, the y is 0. So the length of that is just 1 over square root of 3. But then we're going to have little circles inside here that hollow this out. Right? The little circle is going to go like that. So maybe I'll draw the little circles in blue here. My little circles are going to look like that. And their radii are going to go from here to here. Right? They're just going to go from there to there, from this curve to the x-axis. But when we're on this curve here, y is tangent of x, and on the x-axis y is 0, so my little radii are just tangent of x. All right, so we really just got pi times r squared is our big circles, and then pi times r squared for our little circles, and then minus hollows it out, and then when we integrate from 0 to 6, it adds all those areas together and gives us the solid volume. So what we got to work on doing here now is we've got pi times the integral from 0 to pi over 6. If I square these things, I get 1/3 minus tangent of x. So we got to integrate that. Well, 1/3 is easy to integrate with respect to x. It's just 1/3 x. And then it's going to be minus the antiderivative of tangent of x. Now that's, whoops, and look at this, tangent squared. I squared 1 over square root of 3 to get 1/3. I should have squared the tangent. Now, this makes it a little more difficult, because I was just getting ready to say if we have tangent, I would make it sine over cosine and do u substitution. Tangent, I'm not quite sure of. So maybe on this next page here, I'm just going to do this individually. How do I integrate tangent squared with respect to x? Well, the answer is I don't know. I don't think you can. But if I think back to my trig days, I remember the basic Pythagorean identity. Sine squared of x plus cosine squared of x equals 1. If I go through and I divide every term by cosine squared, I'll get sine squared over cosine squared is tangent squared. And then cosine squared over cosine squared is 1. And then 1 over cosine squared would be tangent. Oh, 1 over cosine squared would be secant squared. And then if I bring this 1 over here, it becomes negative. Tangent squared equals secant squared minus 1. So I can replace the tangent squared here with secant squared of x minus 1. Now I know the derivative of tangent is secant squared. So that means the antiderivative of secant squared is tangent. And then minus the antiderivative of 1 with respect to x would be x. And then if it's an indefinite integral, it's plus some constant. So the antiderivative of tangent squared is tangent of x minus x. So I'll come back here and I'll make this tangent of x minus x. And then I'm going to do this from 0 to pi over 6. So before I evaluate it, I think I'll leave the pi here. And then I'll do 1/3 x minus tangent of x minus x. Well, 1/3 x minus a negative x would be 1/3 x plus x, which I believe is going to give me 4/3 x, and then minus tangent of x. And we do it from 0 to power over 6. So we've got pi times. I'm going to put pi over 6 in for x. So I'll get 4/3 times pi over 6 minus the tangent of pi over 6. If I put 0 in there, I'm going to get 0. It's the beauty of having 0 as one of the boundaries. When it's a trig function, it's not always 0, but the tangent of 0 is 0. So now here I've got pi times. This is going to be 4 pi over 18, which would reduce to 2 pi over 9. And then the tangent of 30, hey, look at this, I got my friend right here. Tangent of 30 is 1 over square root of 3. Right, if we want to get technical, we can go ahead and rationalize that to square root of 3 over 3. Because then that might make this a little nicer, because then maybe we can make this 2 pi over 9, and then multiply this top and bottom by 3 and get 3 square root of 3 over 9. And then pull out a 1 over 9 and get pi over 9 times 2 pi minus 3 square root of 3. And there's our volume. It's that many cubic measurements. And now, wouldn't have been anything wrong in my mind leaving the answer like this. Right? It's the same thing. It's just what looks nicer to you. Right? All right. You guys, the key though is picturing what you're doing and setting up your interval. Okay. So let's do another one. The more we practice, the more we can do on our own. Oh, look at this. Talking about practice. You know, Allen Iverson once talked about practice. He wasn't talking about a game. He was just talking about practice. If you don't know what I'm referring to there, when I say that, I advise you to go on the Google machine or YouTube and type in Allen Iverson's practice interview. You'll get a chuckle out of it. Okay, but this is going to give us some good practice because it's one problem, but it's really 4 problems. Right? We're going to find the volume of the solid if we take the region bounded by the graphs of y equals 2x squared, y equals 0, and x equals 2. We do it about the x-axis, then the y-axis, then the line y equals 8, and then the line x equals 2. So first thing I'm going to do is sketch this. Again, I'm big on what does this look like. Well, 2x squared looks just like x squared. It's just been stretched vertically. So it's going to be a parabola like that. Y equals 0 is the x-axis, and x equals 2 would go through here. So let's see here. X equals 2 would be over here, huh? Ooh, almost messed myself up. Right there's x equals 2. So we've got x equals 2, y equals 0, and y equals 2x squared. We want the region bounded by that. So again, that's going to be bounded by this above, this below, and this on the right. So we're talking about this region right here. Now, since we're going to do this 4 times, instead of drawing it 4 times, I'm just going to take a picture of this. I don't like it when it puts that line in there. It bothers me. See if I can get it without the line. Why is it doing that? If I start from the right and go back to the left, it won't do that. No, still going to do it. All right, I'm giving this thing one more try. All right, I actually paused the video and did it, and I actually did do it on the next try, but I didn't want to get upset if I didn't do it on the next try and have you guys hear me get upset. So we're going to do it 4 times, so I want the graph, I want 4 graphs. Come on. There's another one, and here's my 4th one. Because even though we're doing the same region, we're going to get 4 different solid figures because we're revolving at about 4 different things. So first off here, we're going to revolve it about the x-axis. Right, so this is part 1. We're going to revolve it about the x-axis. Okay, x-axis is a horizontal axis, so I'm going to go to everything in terms of x. The volume is going to be pi times the integral. And the region here is going from 0 to 2, so I'll integrate from 0 to 2. And then we're flush to the axis of revolution, so we don't have to subtract anything out. We just have our big circles, and the radius of the big circles would be from here to here, so it would just be whatever y is here to what y is here, so it would be 2x squared to 0. So my radius is 2x squared. And then the area of a circle is pi times the radius squared, so I square that, and I integrate that with respect to x. All right, so this would turn out to be pi times the integral from 0 to 2 of 4x to the 4th. And I don't like every time I stop writing, my cursor disappears on me. I have to go up here and touch this. Now integrate this, I'm going to get 4x to the 5th over 4. So I'm going to get pi times 4x to the 5th over 4. And I'm going to do it from 0 to 2. So we plug 2 in there, and we get 2 to the 5th, which would be what? 4, 8, 16, 32 times 4. This should have been a 5 down here. 32 times 4 is going to be 128 pi over 5. Cubic units would be the volume. All right, I'm going to pause this for a second and try to figure out what's going on with my cursor. All right, I had to restart the SmartBoard lesson here, so we've lost the last example, but we're going to do now part 2. We're going to go about the y-axis. Okay, so now this is different than any of that we've done so far. If we go about the y-axis, that's going to be going about this axis right here. Right, so now we got to do everything in terms of y. But we're still going to do pi, and then we're going to integrate. Now when I look here, if I go about the y-axis, my region here is not flush against the y-axis. So that tells me I'm going to have big circles, and I'm going to have to subtract out the little circles. And I'm going to do everything in terms of y because we're going about the y-axis. Now, when we go about this, we're going to have a shape that comes around, is going to look something like that. All right, we're going to have this here, and that's going to be solid in. It's going to be like a bowl, hollowed out here. So the first thing I want to figure out is what's the length of the radii of my big circles. If I draw lines like those are going to be my big circles that go all the way around. Okay. So when I draw one of these lines, I'm going from this right here to here, right? So here, and we're doing things in terms of y, here x equals 2, I guess we'll say, and we're going to here where x equals 0. Right? So we're going from 2 to 0, so the big radii are just 2. So the big circles are going to have an area of pi times 2 squared, or 4 pi. Now another thing I should do here too is, where does my region start and stop in terms of y? Well, it starts at 0, because we start at the x-axis, and then it goes to this point right here, where the curve y equals 2x squared equals 2. So I need to figure out, where does 2x squared equal 2? Well, that's going to turn out to be, I take that back. I'm not going to do it like that. That's silly thinking of me. X equals 2, so we already know at this point x is 2. We want to find the y. All Well, I just plug 2 into here to find the y. 2 squared is 4, times 2 would be 8. So they intersect right here when y is 8, so I'm going to integrate from 0 to 8. Right, because we want to do in terms of y, because we want these, if you think about it, these circles start at 0 and they go up until we get to 8. Right, so if we integrate from 0 to 8, it finds the area of every circle going all the way up from 0 to 8. Now we need to hollow it out. This inside part right here is not a part of our region. Circles that would go from there to there, right? Circles that would look about like that are the ones that hollow it out. So I need to know how far is it from the axis of revolution to this function right here where y equals 2x squared. Well, when we do about the y-axis, everything needs to be in terms of y. So I'm going to solve this for y. So I'm going to divide by 2 and take the square root. I guess I said I'm going to solve for x in terms of y. I'm going to divide by 2, so I'll get x is y over 2. Then to get rid of squaring it, I'll take the square root. So x is going to be the square root of y over 2. That's going to be the length of the radii of these smaller circles, or these blue lines. So I'm going to do the square roots of y over 2 squared. Okay. So there's my setup. Pi times 4 squared is my big circles. And I'll write it out. Pi times 4. Integrate from 0 to 8. 2 squared is 4. And then minus here, if I square the square root, I get 1/2 y, or y over 2. So pi times 4 is the area of the big circles. When I integrate from 0 to 8, it adds them all together and gives me the volume of a solid thing that went all the way up. And then pi times y over 2 is the area of one of the little circles that hollows it out. And when I integrate from 0 to 8, it adds them all together and hollows out the whole region. Okay. So let's see if we work this one out. Maybe this might be the last one I work out by hand. The rest I'll do on the calculator to save us some time. But we're going to get pi. And then here, antiderivative 4 with respect to y is 4y. And then minus, this would be y squared over 2 times 2 would be y squared over 4. And we're doing it from 0 to 8. So let's see, we get pi times, put 8 in there, 4 times 8 is 32. Minus 8 squared, 64, divided by 4 would be 16. And then 32 minus 16 would give me 16 pi cubic units. So, because when we go about a vertical axis of revolution, we want to do everything in terms of y. So if we have y in terms of x, we're going to have to solve for x in terms of y. Then our boundaries are where we start and stop our region in terms of y. Now, for part 3, we're going to do about the line y equals 8. So that's going to make even a different shape. So the line y equals 8. Let's see, let's move this down, give ourselves some room. So we figured out in that last part there that these intersect right here at the point 2, 8. So that tells me the line y equals 8 goes right through that point. Let's see if I move this. Look, come on, move up. There's the line right there. So we're going to revolve it about that line. Okay, so now we're going to get some shape that's going around here that looks, do this a little bit, looks something like that, where this is solid again, right? And it's like a bowl but shaped this way, and it's hollowed out in here. Okay, so it's not, we're not flush to the axis of revolution, so we're going to have a washer. Okay, also y equals 8 is a horizontal line, so we want to do everything in terms of x. So the volume is going to be pi. In terms of x, we're going from 0 to 2. Then I'm going to have to figure out the radius of my big circles and then subtract the radius of my little circles, and then integrate this with respect to y. All right, so the big circles are going to have radii that go from the axis of revolution to the function that bounds the region furthest from it, right? So when we come around here, my big circles are going to have radii that are like that. Right, this would actually be a solid cylinder if we didn't hollow it out. Right, the circles would go like that all the way through here. Right, that would give us a solid figure. So we just need to figure out how far is it from 8 to 0. Well, it's just 8, right? So the radius of the big circles is 8. Now the little circles are going to be inside here. They're going to go from here to here. Right? We're going to have little circles that go like that hollow this thing out. So the little circles are just going to go from here to here. So they're going to go from 8 to the function here, which was 2x squared. So the little circles are going to have a radius of 8 minus 2x squared. Right? Because it's whatever y is right here minus y right here to get these radii. And right here, y is 8, and right here, y is 2x squared. So there's what we'd want to integrate. Okay, so now this, let's just say I work this out. This is just grunt work from this point on. You know, we could square this, add like terms, distribute the negative, combine stuff. If we integrate this and work it out, we're going to get 896 pi over 15. All right, maybe on this one here, I'll type it in the calculator real quick just to confirm it. What I would do here, or what we would do, is we're going to options, integrate, and then we're going to do 8 squared. I guess I don't need parentheses there. 8 squared I know is 64. Then we're going to subtract 8 minus 2x squared. That whole thing squared, and then we just did it from 0 to 2. Okay, notice how I left the pi out. I'm just going to get this answer and then tag pi onto it. So I do that, look at that, 896 over 15, which is deja vu all over again. Okay. So you guys, the key to these is setting them up. So let's do this last one here. We're going to revolve it about the line x equals 2. All right, so x equals 2, we already have here. It's this line right here. So we're going to revolve about this line. So if we do that, we're going to get some shape that looks something like this. Right? It's just going to be a solid cone here. So we're flush to the axis of revolution. So we don't have to do, let's see, line y equals, line x equals 2. We're flush to the axis of revolution, so we don't have to subtract anything out. Right? So we can do discs. So this is a vertical line, so we got to do it in terms of y. So we're going to do pi times. Remember, we found the intersection right here to be the point 0, not 0, 2, found to be the point 28. So in terms of y, this is going from 0 to 8. 0 to 8. And then we got to figure out what's the radius of one of these circles. And we square it, and we integrate it with respect to y. Okay, well, when we do these circles, maybe I'll do it in red, right, we're going to go from the axis of revolution to our function. That would be the radius of one of our circles. Right? Then the circles just look like that to give this thing a volume. So we just need to figure out what's the length of one of these lines right here. And remember this also, we worked this out and said x was the square root of y over 2. Because we want everything in terms of y. Because when we have those circles in there, we want them to add all the circles from 0 to 8. Right? Add them all together to give us the volume. So when I look at this, I got to figure out what is the distance from the axis of revolution to the boundary here. Well, it's just whatever x is, back to red here, it's whatever x is right here minus whatever x is right there. Right? That's going to be my line. So right here, x is 2. And then right here, x is square root of y over 2. Square root of y over 2. So, save time, instead of working that out by hand, I'm going to go ahead and just grab the calculator, and I'm going to integrate say 2 minus the square root of y over 2. So let's see, 2 minus square roots of y over 2. I'm going to tag come back here, I should have done this parenthesis there, because I want that whole quantity to be squared. All right, so parenthesis 2 minus the square root of x over 2, that whole thing squared, and then I want to do it from 0 to 2, or 0 to 8. And look at that, 5.3 repeating, which is 16 over 3, or 5 1/3, but I'll write it as 16 over 3 pi. That would be the volume of that resulting figure. So, guys, the trick with these problems is seeing your region and setting up your interval. So the more practice, the more better. So let's try another one here. This time we're going to take the region, we'll do this one with the calculator. We'll say this is a calculator question. We're going to find the volume of the solid formed by revolving the region bounded by the graph of y equals 6 minus 2x minus x squared and y equals x plus 6 about, first off, the x-axis and then the line y equals 3. All right, so I take this back. Let's see if we can do this without the calculator. Okay, let's see if we can picture this graph. Now, the first thing I'm going to do is figure out where these functions intersect. Where does 6 minus 2x minus x squared, where does that equal x plus 6? So I'm going to bring everything to the right-hand side. The x squared becomes positive. 2x plus x would be 3x. And then this is really nice. The 6's cancel. All right, so that's going to be 0. So I can factor out of x, get x plus 3. So my x values are 0 and negative 3. So I know they intersect at 0 and negative 3. And I also know 0, if I put 0 in here for x, I get 6. This line goes through the point 0, 6. So I'm going to sketch, right, the line's just x plus 6. It's just a line. It's got a slope of 1 and y-intercept of 6. So let's say something like that. And we'll move it more this way. Something like that. And I know the parabola is going to intersect it right here. And then it's going to intersect it again at negative 3. Well, if I plug negative 3 in here, I'll get 6 plus 6 would be 12. Minus 9, I'd get 3. So it's also going to be over here. So this was the point 0, 6. And they also intersect at the point negative 3, 3. And then the parabola should just do something like this and come around and do something like that. Okay? Don't have to have a perfect graph, right? Just a nice little sketch there. Now I'm going to take the highlighter. I'll fill in here. Here's our region bounded by those two functions. All right. Now, if I want to find the volume of this, if I revolve it about the x-axis, that's going about this right here. I'm going to go ahead and do this real quick too, is I'm going to take a picture of this. See if I can do it without getting that line in it. Darn it. Look at, that's not even funny. That's not even funny. All right, let's just go with this here. Okay, so we're going to take this region and we're going to revolve it about the x-axis. All right, so we're going to revolve it about this. So we're going to get something that comes over here and sort of matches up over here and then goes around like this, but it's going to be hollowed out in the middle. Now, the x-axis is a horizontal line, so we can keep it in terms of x. So we're going to do pi times the integral from negative 3 to 0. That's our boundaries in terms of x, from negative 3 to 0. And then we're going to have to figure out the radius of our big circles and subtract out the radius of our little circles. And then we'll integrate this with respect to x. So big circles are going to have radii that go from here all the way to here. Right? And then the circles are going to go around. They're going to go from here all the way to there. Right? So these blue lines are the radius of the big circles. Okay, so they're going from whatever y equals right here to whatever y equals right here. Well, up here, y equals 6 minus 2x minus x squared. And then down here, y equals 0. So we could write minus 0, but we don't need to. We get that. Now our little circles that are going to hollow it out are going to go from here to here. All right, the radius of those circles are going to go from there to there, and then we get these little circles that hollow it out. So we got to figure out how far is it from here to here. Well, here y is x plus 6, and here y is 0. So the little circles have a radius of x plus 6. Now, you guys, in the back of my mind, I can hear some of you thinking right now, hey, this is pretty cool, because in all of these, when we go about the x-axis, all we're really doing is finding the area bounded by two curves, and then we're just squaring the two functions, and we're adding a pi, right, to get pi times r squared, pi times r squared. If we were just asked to find the area bounded by these two graphs, we would just integrate from -3 to 0, 6 minus 2x minus x squared minus x plus 6. Right? But now that we're making circles, we have to square the radii and multiply by pi. Now, I'm going to go ahead and just type this in the calculator to save some time, because this lesson's taken a while. And let's see what we get here. So I'm going to integrate 6 minus 2x minus x squared. And then that whole thing's going to be squared. And I'm going to subtract x plus 6 squared. So x plus 6 squared. All right, and then we're going to do it from -3 to 0. 243 over 5. So then I plug the pi in there, and I get 243 pi over 5 cubic units. Okay. That would be the volume of our resulting figure. Okay, now part 2 wants us to do it about the line y equals 3. So I actually did get a picture of this without lines in it. So for part 2, we're going to do it about the line y equals 3. Well, y equals 3 would be a line that goes right there. All right, here's y equals 3. When we found this intersection point, it was at -3, 3, so that line's right there. So now we're going to revolve it about this line. So it's still a horizontal line. So when we find the volume, it's still going to be pi. And we're going to go from -3 to 0. Right? Because we're still going to do it in terms of x, because we're going about a horizontal line. It's still not flush to the axis of revolution. So that means we're going to have big circles and little circles. So we got to find the radius of the big circles and subtract out the radius of the little circles, and do it in terms of x. So this is going to look basically the same. The big circles are going to have a radius that goes from here to here. All right, but now instead of going all the way to y equals 0, they're only going to y equals 3. So it's going to be the value of y right here, which was the 6 minus 2x minus x squared. 6 minus 2x minus x squared. But now we're stopping here, we're stopping at 3, so then we subtract 3. Right? It's whatever y is right here minus y right here is how far we went. Same thing when we do our little circles. Their radii are going to go from here to here. So here, it's on the line x plus 6, right? And here it's on the line 3. So the little radii will have a radius of x plus 6 minus 3. And then we just integrate that. So to save time, I'll plug that in my calculator. And really, the only thing I have to change is just come in here and subtract 3 from both of these things. Right? 6 minus 2x minus x squared minus 3 to match that. Then do the x plus 6 minus 3. Look at that, 108 pi over 5. we get 108 pi over 5 cubic units. All right, now we're really getting somewhere. I feel like hopefully you're getting this down. I want to do one more. Well, you know what? No, we'll save the next one for the next lesson. We've gone about 55 minutes. I feel like hopefully you're getting this down, and I know everybody out there works hard, wants to do their best, so I know you're going to do the homework. You're going to go on the Google machine, right? If you want to see more examples, you're going to look at pictures here of things. You could even Google, if I just switched this to volume disc washer, and I said all, so let's take animations off that. Volume disc washer. Let's do that. Hey, look at this. There's 3,020,000 places you can go to see examples, right? Other people working them out for you. Problems that you could practice. If you just want to look at videos, look at this. There's 436,000 videos. And actually, this girl right here, I'm going to click on this for a second. We got the commercial here real quick for 3 seconds, the ad. Okay, she does a really good job of explaining things. And it's Krista King Math. Okay, you could subscribe to her. There it is right there, https:// that right there. She does a really good job with these kind of things. Okay, so I suggest if you need extra practice, get extra practice. There's a plethora of places you can go for help. There's all kinds of ways you can keep working on this. You guys, somebody once told me, if it's important to you, you'll find a way. If it's not, you'll find an excuse. Hey, I think this is important to you. You guys are going to find a way. Ask me questions. Use the internet. But you guys, most of all, always endeavor to persevere.